5. Row-level locks in MySQL. 1. Overview. Row-level locks are a fine-grained locking mechanism in MySQL, designed to control access to individual rows rather than entire tables. Supported primarily by transactional storage engines like InnoDB, they allow high concurrency by letting multiple transactions work on different rows simultaneously. This is essential for applications that demand data consistency without sacrificing performance. 2. How it works. Row-level locks behave differently depending on the operation. During read operations, for regular select queries, non-locking mode, no locks are applied, ensuring smooth and conflict-free reads. For locking reads, such as select for update or lock in share mode, row-level locks are applied. These locks ensure that the data being read cannot be modified by other transactions until the lock is released. During write operations, when performing update, delete, or insert, exclusive locks are applied to the specific rows being modified. Other transactions are blocked from accessing these locked rows. The locks are released when the transaction is committed or rolled back, ensuring atomicity. Types of row-level locks. Shared locks, S-locks. Multiple transactions can acquire shared locks simultaneously, enabling concurrent reads. However, these locks prevent exclusive locks, ensuring no modifications happen while a shared lock is active. Example, select, lock-in, exclusive locks, X-locks. Only one transaction can hold an exclusive lock on a row at a time, preventing other reads and writes. Applied during operations like update, delete, or select for update. 4. Advantages. 1. High concurrency. Multiple transactions can process different rows simultaneously, significantly improving performance in multi-user systems. 2. Granularity. Only the rows involved in a transaction are locked, reducing the scope of contention compared to table locks. 3. Scalability. Suitable for large, multi-user applications like e-commerce platforms or financial systems where high throughput is essential. 5. Limitations. 1. Lock overhead. Managing locks for thousands of rows can consume server resources and increase latency. 2. Deadlocks. As multiple transactions compete for locks, circular dependencies may arise, causing deadlocks. Example, transaction A locks row 1 and requests row 2, while transaction B locks row 2 and requests row 1. 3. Not supported by non-transactional engines. Row-level locks are unavailable in storage engines like MyISQL, which only support table-level locking. 6. Best use cases. 1. Transactional systems. Applications requiring ACID compliance, such as banking or inventory management. 2. High concurrency environments. Ideal for multi-user applications, where simultaneous access to different rows is common. 3. Selective operations. Efficient for queries targeting specific rows, ensuring minimal locking impact on unrelated rows. 7. Deadlock prevention. 1. Consistent locking order. Always access resources in a predetermined sequence to avoid circular dependencies. 2. Short transactions. Keep transactions focused and concise to minimize the duration of locks. 3. Proper indexing. Use indexes to ensure that only the required rows are locked, reducing unnecessary contention. 8. Summary. Row-level locks are a cornerstone of high-performance transactional databases. They allow MySQL to maintain data consistency while enabling concurrent transactions. Though they offer scalability and flexibility, careful design is necessary to avoid deadlocks and lock overhead. By understanding their behavior and use cases, developers can leverage row-level locks to build efficient concurrent applications,